Good morning all. This is Dr. D. Khalandar Basha working as Associate Professor in Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss the mission language instruction formats of 8086 microprocessor under the course Microprocessors and Microcontrollers. So the slides are prepared by referring the textbooks Advanced Microprocessor and Peripherals by K.M. Gudchandi and IARE, publication Tata McGraw-Hill Public. So mission language instruction formats. So a mission language instruction format has one or more number of fields associated with it. So the first field called as operational code or simply called as opcode field, which indicates the type of the operation to be performed by CPU. Type of operation. The instruction format also contains other fields known as operand fields. So the CPU executes the instruction using the information which reside in these fields. There are 6 general formats of instruction in 8086 microprocessor instruction set. The length of an instruction may be vary from 1 byte to 6 bytes. So first we will see 1 byte instructions. So this format is only 1 byte long and maybe have the implied data or register operands. The least significant 3 bits of opcode are used to specify the register operand if you have any registers. Otherwise, all the 8 bits of opcode and operands are implied. So if it is implied, no need to explicitly specify the register code. Suppose if any register wants to specify, we need to specify the registers in the least significant 3 bits. The next type is a register to register. This format is 2 byte long. The first byte of the code specify the operation and the width of the operand is specified by W bits. The second byte of the code shows the register operand and memory RM by fields as shown in figure. So this is a first byte and this is the second byte. In the first byte, the last digits, that is D0, D1 bits, will specify the width of the operand, whereas D2 to D7, these are given the opcode. For register transfer, here D7 and D6 are 1, 1. D3, D4, D5 will be used as a register code. D0, D1, D2 are for register or memory. The register specified by REG field is one of the operand. The R by M field specify another register or it may be a memory location that act as the second operand. Next, register 2 are from memory with no displacement. So this format is also 2 byte long and similar to register format except MOD field as shown in the figure. The MOD field shows the mode of addressing. The fourth one is register 2 are from memory with the displacement. This type of instruction contains 1 or 2 additional bytes for displacement along with 2 bytes the format of register 2 are from memory without a displacement. The format is shown below. So the first byte as well as second byte is same as that of the previous case. The next subsequent bytes will specify the offset value of the address. So in the third byte, we are going to have the lower byte of the displacement. The fourth byte will consist of higher byte of the displacement. The next type is immediate operand to register. In this format, the first byte as well as the 3 bits from the second byte will be used for register field in case of register to register format are used in the opcode. It also contains one or more bytes of immediate data because it is immediate operand to register. The complete instruction format is shown in the figure below. The first byte will specify the opcode. In the second byte, 3 more bits are reserved for opcode only. D6 and D7 bits are 1 1. D0, D1, D2 will specify either it may be the data may be transferring to a register or memory location that we are writing as R by M. So whatever the immediate data which you are going to have, the lower byte of the data is specified in the third byte. In the fourth byte, the higher byte of the immediate data will be placed. The next one is immediate operand to memory with a 16 displacement. So this type of instruction requires 5 to 6 bytes for coding. The first 2 bytes contain the information regarding to opcode, mode and register or memory fields. So in the first byte we have opcode. In the second byte 3 bits are reserved for opcode, 2 bits for mode and the 3 bits are either register or memory. As it is the memory displacement, we can have the lower byte of the displacement as well as higher byte of the displacement. Here we can have the displacement of 16 bit size, followed by the data 16 bytes. First we are going to place the lower byte of the data. In the subsequent bytes we are going to have higher byte of the data. So these are the 6 instruction formats which are supported in 8086 processor. Now we will see what this R field it is going to indicate, MOT field, W field. So we are going to discuss in detail. So the opcode usually appears in the first byte, but in a few instructions, a register may be a destination in the first byte and a few other instruction it may contains 3 bits of the code in the second byte. The opcode have a single bit indicators. First we will see the W bit. This W bit indicates whether the instruction is to be operated over 8-bit or 16-bit of the data or operands. So if W is equivalent to 0, it indicates the operand is 8 bits. If W is 1, the operand is of 16 bits. Next we have a D bit. This bit is valid in case of double operand instructions. One of the operand must be a register specified in the REG field. The register specified in REG is a source operand if D is equivalent to 0. If D is equivalent to 1, the REG field will use the destination operand. The next bit is corresponding to the S bit. This bit is called as sign extension bit. The S bit is used along with the W bit to show the type of the operation. For example, A 8-bit operation with the 8-bit immediate data operand is indicated as S is equivalent to 0, W is equivalent to S. Whereas for 16-bit case, W is 0 for 8-bit data, that is 8-bit operation. Whereas W is equivalent to 1, it indicates a 16-bit operation. That means the data is also 16-bit size. And S is equivalent to 0, so it is not a signed extension. Whereas if S is equivalent to 1 and W is equivalent to 1, S is equivalent to 1 indicates it is signed extended, whereas W1 indicates it is a 16-bit operation. So the size of the data which you are going to be considering is 16-bit size. The next one is corresponding to the V bit. The V bit is used in case of shift and rotate instructions. That V bit is equivalent to 0. It shifts the count is 1. That is a default shift or rotate. And if V bit is set to 1, then the count we have to specify in CL register, where CL register is the default counter for holding how many shift operation we are going to be performed. Next we will see the Z bit. The Z bit, it is mainly used in REP instruction under string manipulation instruction, which is used to control the loop. So if Z bit is equivalent to 1, the instruction with REP prefix is executed until the 0 flag matches the Z. Next we will see the REG field. The REG code of a different registers, either it may be a source register or it may be a destination register. We already discussed how it is specified, whether it is a source register or a destination register by using the D bit. Next here, the segment registers are only 4 in number, like code segment, data segment, extra segment and stack segment. Hence, we require only 2 binary bits is sufficient to code them. The other registers which are 8 in number, so we require at least 3 bits to code. To allow the use of 16-bit registers, 2 8-bit registers, they are coded with W bit as shown in the table 1. First one is W. So the W bit will indicates what is the size of a register we are going to use. So here 8086 processor, we can use the general purpose register for 8-bit operation as well as 16-bit operation. The 8-bit case which are AL, AH, BL, BH, CL, CH, DL, DH. So as we have 8 8-bit registers, each and every register will be coded with 3-bit data. So 000 indicates for AL register, 001 it is for CL register, 010 it is for DL register, 011 it indicates the BL register. Whereas the register code, if it is 100, it corresponding to AH register, 101 for CH register, 110 for DH register, 111 for BH register. So if you observe the register address code, if MSB bit is equivalent to 1, it is specifying the lower order of the registers like AL, BL, CL, DL. When the MSB bit is equivalent to 1, it specifies the higher order byte of the register, which is AH, BH, CH and DH register. However, as all these are 8-bit register, the W bit will be corresponding to 0 for all these cases. Next, when the W bit is equivalent to 1, it corresponding to the 16-bit data. So the registers which we are going to be refer are 16-bit size. 000 corresponding to AX register, 001 corresponding to CX register, 010 corresponding to for DX register, 011 corresponding to BX register. Whereas 100 it is for stack pointer, 101 it is for base pointer, 110 it is source index register, 111 destination index register. So now here also in the register field, when W is equivalent to 1, the MSB bit if it is 0, these are corresponding to the general purpose register. General purpose registers. When W bit is equivalent to 1 and in the register code, if MSB bit is equivalent to 1, it will corresponding to special purpose registers. These are pointers and index registers. Here in 8086 processor, we have through index registers, two index registers, SI and DI. 3 pointers we have, source pointer, base pointer and instruction pointer. The instruction pointer is corresponding to the instruction. So usually we won't specify in the opcode field. So to find out the mode and RM fields of a particular instruction, one should first decide the addressing mode of the instruction. The addressing mode depends upon the operand and suggests how the effective address may be computed for locating the operand if it is lies in the memory. So the RM column and addressing mode row field specify the RM field, that is registrar memory field, while the addressing mode column specify the mode field. So the D8 and D16 represents 8 and 16 bit displacements respectively. The default segment for addressing modes using base pointer and stack pointer is stack segment. For other addressing modes, the default segments are data segment and extra segment. Now we will see in this table the different addressing modes of the 8086 processor. So the R by M field 000, 001, 010, 011, 100, 101, 110, 111. 8 we can have. Next, the MOD build, if it is 00, it indicates no displacement. If it is 01, 8-bit displacement, 10, 16-bit displacement. If MOD is equivalent to 11, then it is indicates the register as operands. When the R by M field is 000, here we can have the displacement in BX register and SI register. 001 BX register and DI register. 010 base pointer and SI register. 010 BP, that is base pointer and destination index register. 100 is for source indexing. 101 DI register. 110 16-bit displacement. 111 the BX register. So here we don't have any displacement. Whereas with 8-bit displacement, for this field, the additional, the 8-bit displacement will be added. Whereas for 16-bit, the 16-bit displacement is added, that is D16. And here if you observe, these two are, one is base register, the second one is index register. These are base index addressing mode, whereas these are two corresponding to indexed addressing mode, whereas the last one indicates it is register index addressing mode. Next, already we have checked the register field. When W is equivalent to 0, all the 8-bit registers are used in the register position. If W is equivalent to 1, general purpose registers, 2 pointers and 2 index registers we can have. So the data segment register is the default data segment register when a data is to be referred as operand. And the code segment is the default code segment register for storing program codes, which are executable codes. SS is the default segment register for stack data access and operations. Next, extra segment register ES is the default segment register for the destination data storage. So all the segments available can be read or written as data segments by newly defining the data segment is required. So there is no physical difference in the memory structure or no physical separation between the segment areas. They may or may not overlap with each other. So overlap means if I am corresponding to this 64-bit K location is assigned as one segment, again here we are taking one more portion. This you can take as segment 1. This 64K you can take as segment. This is called as overlapping. Few portion of the memory locations will lies in two different segments. Suppose if the memory I have, this is segment 1 and this block you can take as segment 2, each are of 64K, each are of 64K. Now we don't have any overlapping. So thank you. So in this session we have discussed the mission language instruction formats. In 8086 processor, the instruction formats may vary from 1 byte to 6 bytes. In these instructions, what are the various fields we are having? So how to recognize or how to write the equivalent opcode for any instruction depending upon the register, what is its size, whether it is signed extension or not, and what is the addressing mode. Depending upon that, we can write any instruction opcode equivalent. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.